Okay, so this is the third part of linear equations. Like you have seen that elimination method. In Gauss-Jordan elimination method, what we do, for example, you have a system of linear equations 4x y minus z equals to 3, and then let's say I'm writing any three linear equations. It could be any other, not necessary. Let's say 3z equals to 0. Now we write them in a matrix form. We write their coefficients, or we write them 4x plus y minus z, x minus y plus z, 2x plus y plus 3z equals to 3 0 0. Now or the other way to write it, we just write their coefficients. For example, the coefficient of x is 4, the coefficient of y is 1, the coefficient of z is minus 1, and then there is the constant. Then coefficient of x is 1, coefficient of y is minus 1, coefficient of z is 1, and then 0. Similarly, the coefficient of x is 2, 1, 3, and 0. So this is how we form this matrix, and our objective is to transform this side of the matrix into this form, which is called the identity form, as you have seen in college algebra and in fundamental mathematics. So this is called identity form. We have to transform this form into this form, and this is called identity. And on the diagonal it must be 1 and rest of the elements should be 0. So this is how we read the solution: x equals to 3, y equals to 4, z equals to 5. So this is the position of x, this is the position of, this is position of x, this is position of y, this is position of z. So x, y are 0, so x equals to 3. So this is how we write it exist. But when we have all rows 0, in that case we will say that there exist infinite many solutions, and later on in examples we will see that how we can find those infinite many solutions. So first of all, we reduce row echelon form, or so-called Gauss-Jordan form. Each row consisting entirely of zeros is below any row having at least one non-zero element. The leftmost non-zero element in each row is 1, like on the diagonal, and the leftmost one in any row is the right of the leftmost one in the row above. Okay, what it says? It says that if you have this form, this is inconsistent form, no solution, because 0 is not equals to 6. If you have this form, that means you have unique solution. And similarly, in this form you can have infinite many solutions. We will discuss them later, how does it happens. Anyways, these are all reduced row echelon form. Okay, so now here is the example. For example, this is a system of linear equation. We write it in a augmented matrix form. This is called augmented matrix form. So we write coefficient of x here, coefficient of y here, coefficient of z here, and constants here. Now coefficient of x is 2, coefficient of y is minus 1, coefficient of z is 1, and 5 comes here. Similarly, coefficient of x is minus 1, coefficient of y is 2, coefficient of z is 2, and constant come here. This is called this is called augmented form of a matrix, like this. Now our aim is to transform this side of the matrix into this form: 1 0 0 0 1 0 0 0 1. Whatever we get here, we don't care. That would be our solution ultimately. To do so, you see, we need to do it systematically. First of all, you see here we have 1. So we need to transform this element into 1, which is already 1, so we don't need to do anything. So we will keep it as it is. We already have a 1 in the diagonal position of first column. We are talking about this. Now we want zeros below the 1. Now we want zeros below this one. Now this element and this element should be 0, and adding the results to row 2. Now what we need to do, we will multiply this complete row with -2. It will become -2, -2, 2 and 4, and we will add the result into this second row. This is called row operations, and this is how we write. We want to bring change in row 2. This is our row 2. How we will bring this change? We will multiply row 1 with negative row 1. We are multiplying row 1 with -2, and it will give us a new row 2. So multiply row 1 with negative, so it will become, so now -2, this -2 plus 2, it gives us 0. This -2 and -1, it gives us -3. Similarly, this 2 and 1, it gives us 3, and this 4 and 5, it gives us 9. Similarly, we repeat this operation, and what we do now, we have to convert. In the next slide you will see it. Here you can see this is what we got. Now the second 0 can be obtained by adding row 1 to this is just an explanation of the operation which I did. Now I need 1 here, because we need to convert it into 1 0 0 0 1 0 0 0 0 1. Whatever we get here in the third column, we don't care, that would be our solution. So I need, after making 1 here, we brought 0 downstairs. Similarly, move diagonally. Next aim is we need to get 1 here. To do so, I divide this complete second row with 3. I divide it with -3, so it will become +1. So if I do so, I will get 1 here, -1 here, and -3 here. So let's see, we do this operation in the next here. This is the explained operation which I just performed. We divide this complete row with -3 and we get a new row 2. Now with the help of this one, we bring 0 here and we bring 0 here. How we will bring 0 here? Top of this one, I need to bring change in row 1. How we will bring this change? I will multiply -1 with row 2 and add the result in row 1. It will give us a new row 1. So I multiply row 2 with -1, so it will become -1, 1 and 3. So this one will add into this, it will become 0. This one will add into -1, it will be 0. This 3 will add into -2, it will give us 1. So let's see, they did this other operation first. They brought change here first, they brought make it 0 here. So likewise you can do it, and here you can see that with the help of this one we are making 0 here and 0 here. You can also make 0 here as well, and when you do so, ultimately you will get this form. Now this x is your 1, y is -1, and z is 2. So that is our solution. This is how we write our solution.